My name is Dr. Mike Murphy. I'm an assistant professor of computer science and information systems at Coastal Carolina University. In this lecture, I will introduce paging and related topics, including logical addressing, address translation, and the translation look-aside buffer. Paging provides a mechanism for sharing memory among multiple user space processes at the same time. This mechanism improves upon simpler algorithms, such as static partitioning and direct power of 2 methods, by allocating fixed-size pages of memory to processes. The key to effective memory utilization with paging is that each process is given its own logical memory space. In other words, each process has its own view of memory with its own address space. The addresses that the process sees are called logical addresses. These logical addresses are divided into fixed-size pages. Each process in the system receives its own private set of pages with private memory addresses. When a process accesses memory using one of its logical addresses, the CPU translates the logical address into a physical address. Physical addresses refer to locations in system memory. For performance reasons, translation is done in terms of memory frames, or fixed-size regions of RAM. The base frame size is normally 4 kibibytes, although this can vary by hardware device, and most hardware can support multiple different frame sizes. Operating systems normally use logical page sizes that correspond to supported hardware frame sizes. Again, 4 kibibyte pages are a typical base size. On x86 and x86-64 systems, the Linux kernel can support so-called huge pages, which can be as large as 1 gigabyte when using the newest AMD and Intel CPUs. The key advantage to paging is that it eliminates the issue of external fragmentation. Since the CPU is translating logical page-based addresses into physical frame-based addresses anyway, there is no need for the physical frames to be contiguous. As a result, we can store a data structure in process memory using pages that are logically contiguous. However, when these logical pages are mapped to physical frames, the frames may be scattered throughout RAM. Notice that the distinction between a page and a frame is a matter of terminology. A page refers to a block of logical memory, while a frame refers to a block of physical memory. For now, pretend that there is a one-to-one correspondence between logical pages and physical frames. We'll make things more complicated later. The key to making page translation efficient is that the CPU contains special hardware called the Memory Management Unit, or MMU, which performs the translation operations. In this diagram, the process accesses memory using logical addresses, which are divided into pages. When requests are made using these addresses, the Memory Management Unit on the CPU translates the logical address into a corresponding physical address. The resulting physical address will be to some point of a physical memory frame. Note that individual memory addresses within pages or frames still remain contiguous, which is important because the MMU translates page numbers to frame numbers, leaving the offset to the memory location within the page unchanged. As shown in this diagram, we can divide a logical address from a process into two components, the page number P and the offset D. When the MMU is asked to perform a translation, it consults a data structure called a page table, which provides a mapping between page number and frame numbers. Using this information, the MMU constructs the physical address by using the corresponding frame number, represented here by the letter F, in place of the page number. Once again, the offset to the particular byte within the page or frame is left unchanged. A particular byte in RAM is actually addressed using the frame number and offset into the frame. However, to the process, this memory access appears to occur using a logical memory address, which is conceptually divided into a page number and offset. The offset component is not changed by the MMU, but the page number is replaced by the physical frame number. In order to perform the translation from page numbers to frame numbers, the MMU must consult the page table. The page table is a data structure that is itself stored in RAM in the kernel memory space. Storing the page table in RAM leads to a major problem, since every MMU translation would require a lookup. Since the lookup requires a memory access, each process memory request would actually require two physical memory accesses. This situation is especially troublesome because a memory access occurs both upon accessing data and upon reading the next instruction to be executed. Without some additional hardware to resolve this problem, system memory performance would be effectively cut in two, greatly reducing the overall performance of the system. The solution for eliminating the double memory access issue is to add a component to the CPU called the Translation Look-Aside Buffer, or TLB, which stores some page-to-frame mappings. Some TLBs also provide room for address space identifiers, which aid in implementing memory protection. The TLB is a piece of associative memory, meaning that it can perform rapid, parallel searches, resulting in constant time lookups for page translation. This memory is exceptionally fast, meaning that it is also quite expensive. As a result, TLB sizes are typically limited from 8 to 4096 entries. The addition of the TLB provides a potential shortcut for performing address translation. Instead of immediately searching the page table, the MMU first searches the TLB. If the page-to-frame mapping can be found in the TLB, then it is used to perform the translation from page number P to frame number F. This situation is called a TLB hit. A TLB miss occurs whenever the page number is not present in the TLB. In this case, the MMU must search the page table to locate the appropriate frame number. The CPU and operating system employ various policies to determine when to store a page-to-frame mapping in the TLB. A simple policy would be to use a first-in, first-out policy that replaces the earliest entry in the TLB with the newest entry upon a TLB miss. Other, more complex, and potentially better policies also exist.